Hi everyone, welcome to Chapter 8, Bivariate Correlational Research. So we're going to go ahead and talk this week about correlations and how those are used to kind of look at relationships between different variables. Let's go ahead and jump in. So this week we'll be covering Chapter 8, Bivariate Correlational Research. In this chapter, we're going to talk about relationships between two variables and how we can use correlational research designs to provide us with information about those relationships. So this is kind of the first chapter where we'll be discussing specific research practices and can kind of be seen as a shift from more theory-oriented content to practical applications of our material. This chapter is divided into two main parts. The first part is an introduction to bivariate correlations, where we'll discuss generally what they are and how they're performed. The second section examines how claims associated with correlations are interrogated. So we'll discuss how we can interrogate such claims using the same four validities we've discussed in previous chapters. So let's start off by simply talking about what a bivariate correlation is. So bivariate, or two variable correlations, are simply that, a correlation between two and only two variables. You can see here in the table data from a study that examined marital satisfaction. Here we see participants responded both with their marital satisfaction as well as where they met their spouse, either in person or online. We might use this set of data to answer the question, is there a relationship or correlation between the way someone met their spouse and the level of their current marital satisfaction? When we perform a bivariate correlation, we are necessarily looking at two variables, but what form those variables take will depend on what they're asking. For example, on the previous slide, one of the variables was rating a marital satisfaction on a 7-point scale. Since this variable can range on a scale, it's considered a quantitative variable. It has a quantity of something that it is measuring. However, another variable measured was the location that people met their spouse, either online or offline. This variable isn't quantitative since it's not measuring some amount of something. Instead, it's what we call a categorical variable. It simply measures what category a data point falls into. Next, we're going to discuss how we need to keep in mind what type of variables we have and how we would go about examining the relationships differently based on whether or not we're looking at two quantitative variables or if we have one or more variables that were categorical. Let's first discuss how we can examine associations between two quantitative variables. Here we have a graph of data points from a study which examined the relationship between well-being scores and percentage of deep talk. We can see from the data, as well as the correlation line, that this relationship is positive, such that higher scores on well-being tend to be associated with higher percentages of deep talk. It turns out that the correlation coefficient here, or R, is equal to 0.28. Remember that R is a statistical value that represents the degree of association or correlation between two variables. It can range from -1 to +1, which indicates a negative or positive relationship respectively. And scores close to 0 indicate that there is no relationship between the two variables. Positive values of R indicate a positive relationship such that higher scores on one variable are associated with higher scores on another variable, and lower scores are associated with lower scores. Whereas negative R values mean high scores on one variable are associated with low scores on the other variable, so opposite directions. So in general, when we're looking at the relationship between two quantitative variables, we're going to be looking at the individual values of each data point. This can be depicted as a scatter plot, like what was just shown in the previous example. We can then correlate these two variables and find a coefficient value, or R value, that tells us the direction and strength of the relationship. Next, let's talk about what changes when one of our variables is categorical. We'll first talk about the changes we'll see in the graphical form of our data representation, as well as how we can view and analyze our associations in a slightly different way. At the end of the day, it's important to remember, though, that as long as we're measuring the relationship between two variables, regardless of their type, we're still performing a correlational study. Remember back to the example of the comparison of marital satisfaction to the location of where people met their spouse, either online or offline. Notice that the first variable, marital satisfaction, is quantitative, and the other variable, where a person met his or her spouse, is categorical. The graph on the left is a scatter plot representation of this data. Notice that since the bottom variable is categorical, our data points simply form two vertical lines. We can still perform a correlation on this data, and it turns out that we would get a correlation value of these two variables, in this case of r equals 0.06, which is a fairly small correlation. It's much more common, though, to plot the results of an association between one quantitative variable and one categorical variable in a bar graph like the one pictured on the right. In a bar graph, each individual is not represented by a data point. Instead, we show the graph or the mean of each group, in this case for marital satisfaction for those who met their spouse online, and the average for those who met their spouse offline. Here, the online mean is slightly higher than the offline mean, corresponding to a weak association between the two variables. We'll see in later chapters that a better statistical approach to use with data of this structure is actually a t-test. So remember, association claims can be graphed using scatter plots or bar graphs, and they can be made using R or differences between means. When making an association claim, the kind of graph you make or the kind of statistic you use isn't important. What is important is having two measured variables. Now let's shift to discussing how we go about interrogating association claims. Remember here, we're going to use the same four validities we've discussed in previous chapters to interrogate our claims. We'll talk about construct, statistical, internal, and external validity here. For association claims, the most important validities to consider are construct validity and statistical validity. Recall that construct validity is how well your variables measure the construct or idea that you are intending them to measure. It's important to think about the construct validity of both of the two variables in an association claim. You need to ask yourself how well each variable was measured. Does it have good reliability? Did it measure what it intended to measure? And what evidence is there for its face, concurrent, discriminant, and convergent validities? When considering the statistical validity of an association claim, you need to consider the strength and statistical significance of the relationships. If there were any outliers, was there a restriction of the range, and the possibility of a curvilinear relationship? Let's go into a bit more detail on some of these specific questions. When we ask ourselves about the strength of a relationship, we're describing the effect size. Let's look at the two graphs here. Both of these show positive associations, but which scatter plot shows the stronger relationship, graph A or graph B? Some associations are stronger than others, and the effect size describes the strength of this association. In these graphs, both associations are positive, but B is a stronger association. R would be closer to 1 than in graph A. Therefore, B depicts a stronger effect size. You can see the visual difference between the data points in the two graphs. Graph B has a more narrow band of points, which is how we can tell it has a stronger relationship than graph A, which has more spread out points. Let's now discuss how we evaluate effect sizes. When we think about effect size in general, we can think of it as a measure of how well the data can predict real-world outcomes. Effect size can also indicate the importance of a result. A larger effect size is usually considered more important than a small one when all else is equal. However, there are some exceptions. Depending on the context, even a small effect size can be important. For example, the correlation between the personality trait of agreeableness and the success of a single social interaction may be only 0.07, but if this effect is aggregated over the course of a couple hundred social interactions, well, an agreeable person may end up being more popular than a less agreeable person. Another example might be in baseball. Here, star batters are only slightly better at getting on base than average batters, typically an R value of about 0.05. But over the course of a full season of baseball with more than 550 chances to hit the ball, this seemingly small effect size translates into many more runs. We can also think about an effect size by comparing it to well-understood benchmarks. The average effect size in psychology is around R of 0.20 and rarely as high as an R value of 0.40. Based on the descriptions in this table, we can see the general distribution of effect sizes for psychology-based studies. Often the largest values of effect size in the 0.4 range and above may be too good to be true and might just be an error due to small sample sizes, among other reasons. When interrogating association claims, we should always ask ourselves if there could be the possibility of an outlier. An outlier is an extreme score, or perhaps a few, that lies far away from the rest of the scores. The two scatter plots on the top are identical except for the outlier in the upper right-hand corner in the left scatter plot. The correlation coefficient in the left graph is 0.37, and for the right graph, it's 0.26. Outliers can cause problems for association claims because they may exert a large amount of influence. In bivariate correlations, outliers are most problematic when they involve extreme scores on both variables. Outliers are also most influential when the sample is small. So the two scatter plots on the bottom, once again, are identical except for that outlier. Removing the outlier here changes the correlation from 0.49 in the left to 0.15 in the right, which is much bigger than the change from 0.37 to 0.26 that we saw in the top figures. So we can see from this example, outliers can have far-reaching effects on the conclusions we draw from our data. Again, it's important to consider the possibility of outliers and check when you're conducting your own research to make sure there are none. If you do come across an outlier in your own research, it's often reasonable to remove the data point to increase the accuracy of your analysis. It's also important to question if there might be a restriction of range in our data. Restriction of range is when there isn't a full range of scores on one of the variables in an association. A restriction of range can make the correlation appear smaller than it really is. If you look at this graph, you'll see that the two variables are college grades, measured in GPA, and SAT scores. The data are from a highly selective college that only admits students with high SAT scores. A plot of the correlation between college grades and SAT scores for students at this college yields a positive relationship, but the relationship doesn't appear to be very strong. If we were to instead look at the relationship between SAT scores and GPA among all students in the US, well, the relationship would likely look a little bit different. So if we look here, SAT scores range from 400 to 1600, but this particular college only admitted students who scored 1200 or higher. So you can see this cutoff point in the vertical dotted line. So the range is restricted to 1200 to 1600. If we extrapolate from the top scatter plot, we can see what the scatter plot would look like if the range was not restricted in the graph on the bottom. In the top scatter plot, the value of R is 0.33, whereas in the bottom scatter plot, where the range is not restricted, the correlation is stronger with an R value of 0.57. So what can researchers do about restriction of range? Well, there are statistical techniques that allow correlation for restriction of range, or researchers can recruit more participants to try to widen that range. We may also want to ask if the relationship between our two variables might be curvilinear. A curvilinear association is one in which the correlation coefficient is 0 or close to 0, and the relationship between two variables is not a straight line. Take this example among visitors to a haunted house. The more scared people felt, the more they enjoyed the experience, but only up to a point. After that sweet spot, the relationship reverses direction, such that as people become very scared, their enjoyment ratings actually drop. This curvilinear association is not captured adequately by a simple bivariate correlation coefficient, which can only depict a straight line. Although it's not a priority to interrogate internal validity when making an association claim, we still want to consider internal validity because we want to be aware of the temptation to turn an association claim into a causal claim. One of the most important things to remember for association claims is that correlation does not mean causation. In order to make a causal claim, a study has to satisfy these three criteria. Number one, covariance. There must be an association between the cause variable A and the effect variable B. Number two, temporal precedence, or the directionality problem. The causal variable A must come before the effect variable B in time. And finally, internal validity, or the third variable problem. Is there a third variable, C, that is associated with both variables A and B independently? And if so, we can't infer causation. When we come up with a third variable explanation for an association, how do we know if it poses a problem for internal validity? Let's look at these two examples. In the first graph on the left, we see the relationship between hair length and height, separated out by gender. If we look at all the data together, we see there appears to be an overall negative relationship between hair length and height. However, women, orange dots, are both higher in hair length and lower in height compared with men, who are represented by the blue dots. Within each gender group, there is no relationship between these two variables. This outcome means that gender is really the reason hair length and height are negatively correlated, and thus a problematic third variable here. On the other hand, if we look at the graph on the right, we see the relationship between weight and height. Here, women, the orange dots, are lower in both height and weight than men, the blue dots. However, within each gender group, there is still a positive relationship between height and weight. So this outcome means that gender does not actually pose an internal validity problem in this relationship. Height and weight are still correlated even within the two gender subgroups. Finally, let's discuss external validity. Does the association generalize to other people, places, and times? It's important to remember here that the size of the sample does not matter as much as the way the sample was selected from the population of interest. If a bivariate correlation study fails to use a random sample, it should not cause us to automatically reject the association. Instead, we can accept the results as they are and save the question of generalizability for another study that tests the same variables in a different population. Also, many associations generalize to samples that are very different from the original sample. Here we can see that older adults, represented by O, might spend less time in deep conversation than college students, represented by Y, and they might have lower well-being, but the association between the two variables within each sample of people still exists. When the relationship between two variables changes depending on the level of another variable, that other variable is called a moderator. For example, let's consider a study on the correlation between professional sports games attendance and the success of the team. Using data gathered over many Major League Baseball seasons, it was determined that in cities with high residential mobility, there was a positive correlation between success and attendance, indicating a fair weather fan base. In cities with low residential mobility, there was not a significant correlation between success and attendance. We say then that the degree of residential mobility moderates the relationship between success and attendance. Let's look at these graphs where we can see how a city's degree of residential mobility moderates the relationship between local sports team success and attendance at games. Each dot represents one Major League Baseball season. The Arizona Diamondbacks are based in Phoenix, a city with high residential mobility, and that pattern shows that people are more likely to attend games there when the team is having a winning season. Pittsburgh is a city with low residential mobility. That pattern shows that Pittsburgh Pirates fans attend games regardless of how winning the season is.